Divergence example part 2. So I already did part 1, link down below, and I showed that the divergence theorem, which says that del.f volume integral over some surface is equal to the flux over that surface, that same function f. And yeah, this is Gauss's law does come from this. Or you can show that Gauss's law is the same thing as this. And I used the function, the vector function, x squared y in the x direction, 2xz in the y direction, and z squared minus 2y in the z direction. I just made that function up just for fun. And then I did this surface, so this cubical surface that's 1 by 1 by 1 with one origin at the one corner at the origin, the other one at 1, 1, 1. And so when I did that, I did the flux, I did all the things. I found that both sides, this was 3 halves, and this is 3 halves, and so both sides work. Okay, so I want to do this in Python, and it's a cube, so I could do this in a very nice numerical way, but I want to visualize it. So I'm actually going to do a trick with called Monte Carlo calculation, and you don't have to do that. It's just kind of fun. Okay, so here is my cube. X, that's y. And I'm doing x, y, and z this way because that's the way it appears in Python. And so here is my box. Like that. And let's think about the volume integral first. So what I'm going to do is to break this into n pieces. N equals 100, let's say. And so for 100 times, I'm going to put a random sphere in here, where each one of those spheres is at some random location, so they'll be uniformly distributed, not perfectly, but close enough. And each one of those spheres would have a volume dv equals 1 over n. And so dv 1 over n that's because the volume of the whole cube, I want these 100 points to have the same volume as the cube, even though they don't all perfectly line up. Some of them may overlap. Some may extend a little bit beyond the boundaries, but that's fine. At the end of the day, when I add up all the volume of the cubes, these spheres, I get the volume of the whole cube. And that's why that's 1. That's 1 times 1 times 1, so 1 cubed. And then I can draw them with the correct radius, because the volume of that sphere is going to be 4/3 pi, we'll call that r cubed, right? That's the radius of that sphere. So r is going to be equal to, let's say r cubed is going to be equal to 3/4. So you multiply by 3, divide by 4, divide by pi. That's true, right? Yep. And then so r is just going to be the cubed root of 3 over 4 pi n. Okay, so that's all my spheres. But what I'm going to do to calculate I'm going to calculate the divergence, which I already had, so I'm going to still use this. F equals, where did my function go? There it is. I can use the same function, f x squared y, 2xy, z squared minus 2y. And I'm also going to use the same divergence, or the del.f. I did this before. It's just going to be equal to, what was that? It's just 2xy plus 2z. So then what I can do, if I want to calculate the volume integral, let's call this Q. I'm going to call it big Q because it's kind of like the charge. Okay, it's kind of like the total charge. So I can say dq is going to be equal to dv times del dot f. So for each of these points, I can calculate what this is, evaluate at my x and y value for that sphere, and just get one single value. And then I can do that for all 100 points and add them up and get the total. And that will be the volume integral. And yes, you could break this into little boxes. I've done this before and add up all the boxes, but I like this new Monte Carlo way. Now in Python, what we do is use the variable random. This returns a variable a number between 0 and 1. So I can make some RT vector of random. And so since these all go from 0 to 1, this will be in the box. I don't have to worry about it. I'm going to make 100 points that will be in the box. And I calculate DQ for each one of them, add them all up. And that's it. Okay, so now what about for the flux? Now for the flux, we're going to not make a... Let's look at the flux for just one surface. And we're again going to use Monte Carlo. So suppose I have one of the surfaces right here. Instead of making spheres, I'm going to make circles. They're actually going to be cylinders. So again, I can say in, we'll call this in F for flux. The number of flux is equal to 100. I want the area of each one of these such that dA is equal to the area of the whole thing, which is 1 squared, divided by NF. And that's going to be equal to the area of a circle, pi r squared. So in this case, r is going to be equal to the square root of 1 over pi NF. Now, I also need, since it's a cylinder, I actually need to set the unit vector for each cylinder. In Python, a cylinder looks like this. So it has three attributes. One is the position, is the location of one end. The axis is a vector from the position to the end, and then I have the radius, r. So those are the three things. In this case, I want the axis to be pointing in the direction of n hat. So I can pick those n hats, right? I know what n hat is for each surface. I already wrote it down before. If I have a cube like this, on this side, n hat is going to be the vector 1, 0, 0. In the x direction over here, it's going to be negative 1, 0, 0. And then down here, it's going to be 0, negative 1, 0. Over here, it's going to be 0, 1, 0. And then the z and the negative z. Okay, so I can do that. And then to find the flux, I'll call that d flux. It's going to be equal to f dot n hat. I can do the dot product times dA. And so what I'm going to do is calculate the value, the vector value of f at all those places, assume it's constant over the whole circle, do this, and then find the total flux is just going to be the sum of the individual fluxes. And then we'll see if the two things work the same. And again, that's what we need to do. Okay, now the other trick here is if I have a cube, then I can I only need two random numbers, because I can set x, y, or z equal to 0 and 1. I only need to have two of them to uniformly distribute them. Okay, let's get to it. I know you're excited. I've already wasted 8 whole minutes talking about that. So here we are in Python. I'm using GlowScript vPython. If you're not familiar with this, it's just it's web-based. It's a little bit easier to get into. You don't have to install anything, and that's kind of awesome. Okay, let's do the volume integral first. So I'm going to say n equals 100. And just to show you how this random thing works, let's say n equals 10 and n equals 0. So little n is my counter. So I can do this. While n is less than n, print n, and then n equals n. I don't need to do that. Let's say print random, and then n equals n plus 1. So I need to increment n every time I count 1. So this will just print 10 random numbers between 0 and 1. There you go. So that's showing you that it does work. I'm not making stuff up. Random is a real thing. Okay. So now I want to, I don't want to print that. I want to make some random vectors. I messed that up. Okay. So let's just say RT, I'd like to call it RT for a random vector, is a vector random, random, random. And let me make this whole thing bigger. There, is that better? Can you see better now? Okay. So that's my random variable. Up here, I want to calculate dv is going to be equal to 1 cubed. It's a 1 by 1 cube divided by n. And then rv, that's the radius of the volume element. I already said what that was going to be, and I can't remember already. I said it was equal to the cube root, which I left off the cube to see that. So it's going to be 3 divided by 4 times pi times n. All of that raised to the 1/3 power. And that will make my spheres appropriately sized. So I have my random variable. I want to put a sphere there. So I don't have to actually name it, but I do want to draw it. I want to show it. So I'm going to say sphere position equals RT, radius equals RV, and let's just leave it at that. This should make 10 random spheres in a box. And that doesn't look very 10-ish, but I think that it is. And let's change this to 100. And now if I change this to 100, each sphere is going to get smaller. Yeah. So that's boxish. Let's just go to 1,000, right? Okay. That's a box. Oh, wait. Did you say you wanted to go to 5,000? 5,000. That's pretty nice. Okay. Let's do this. Let's do this. Opacity equals 0.5. So they're partly transparent. Let's see what that looks like. And that's just an artistic choice. Oops. Something didn't like that. Okay, don't do that. I don't know why I didn't like that. Okay, let's just turn off the opacity, not anger the Python gods. RV. Should I save this? I should probably save this, don't you think? Okay, let's just make that a little smaller. Let's run this. Let's put this back to 1,000. I think I just got it. It's just too much for it to handle. Okay, so let's call this Divergence Theorem 1. Save. Okay, now I'm going to calculate the volume integral, but let's just first go ahead and do this. Def f RR. So I want to define the vector function, and I'm going to call it f. So then I just need to return my vector function. So I'm going to return the vector. Now over here I'm looking at my vector function x squared y. So that's RR is a vector that I pass to the function. It's going to return a vector. So I need the x coordinate of that vector, which is RR dot x. So it's going to be RR dot x squared times y, which is RR dot y. That's the x component. The y component is going to be equal to 2 times RR dot x times RR dot z. And then the z component is going to be equal to RR dot z squared minus 2 times RR dot y. So now I don't have to type all that stuff out. I can just say f of the vector location and return it to me. I also need, let's make another function. I need let's say def del f, and I'll give it a function RR, and then I'm just going to return the del of f, which I said was, oh my gosh, where did it go? I had it right here. 2xy, so it's going to be 2 times RR dot x times RR dot y plus 2 times RR dot z. Okay. So I make that function. I make my random location. I need to do del dot f, which I have, times dv, which I have. dv I already have, it's this constant number. So let's go up here and say this. Q equals 0. So the total volume is going to be Q. And then I'm going to say, after I draw the sphere, I'm going to say dq equals del def. No, I want this to be called del f, not def l. Del f. What? Del f. So let's call this del f of RT, right? I need to give it that vector location. Now I have my x and y value times dv, which I already have. And then I'm going to add that to the total. Q equals Q plus dq. And let's just run this. And I'm going to go ahead and print Q. Let's put Q equals Q. And it didn't print. Can't, okay, that del F, del F. What did I call it? Del F. There it is. Okay, so Q, I get the wrong answer. I said it was, no, I did 3/2. I said it was 3/2. So is that 3/2? Let's see, let's just print. Print 3/2. That is, okay. I knew that, 1.5. Okay. And then if I want to change this to 5,000, and I don't even need to draw these spheres. I could take this part out. And it'll still work. And then every time it's going to be a little bit different, but it's always close, right? And that's only 5,000 data points, and that's not that many. Okay, but I do want to draw them. I just kind of like them. They make me a little happy. Okay, so now we need to do the flux. Now we do need to do this 6 times, and instead of doing something clever, I'm just going to do it 6 times. Okay, so I'm going to start with the side 1, looking at my box from before. That was, let's just do x equals 1, the side where x equals 1. So let's say phi equals 0, in f equals, let's say 1,000. And then n equals 0. So n equals 0 is still going to be my counter. I'm going to need to reset that every time. So let's make some, let's say dA. I do need that. It's going to be equal to 1 squared divided by the number of pieces in f. And then RF is going to be equal to the square root of 1 divided by pi times nf, which I didn't have to do it that way, but I did. That's the radius of each sphere. So let's draw these spheres. Actually, I'm going to turn off this so that we can see this better. Okay, while n is less than n, colon, n equals n plus 1. If you don't do n equals n plus 1, it's going to go on forever, and that's just embarrassing. So that I'm going to make a random variable, RT, I'll still call it RT, is going to be the vector in x is equal to 1, right? So I don't need to randomize that variable, it's 1. But I do need to randomize random the y and the z. And then what I'm going to do is to put a cylinder there. So I'll put cylinder position equals RT, radius equals RF, axis, oh, here's what I need to do. Axis equals n hat. And let's put up here, n hat equals 1, vector 1, 0, 0. That's the, if I'm on the x equals 1, n hat is in the positive x direction. So that's going to be n hat, and that should do it. Let's just do 100 first. You always want to do something small. N, this should be less than nf. Okay. Oh, I did an axis. Okay, so my it did work, but it just made the length of each axis 1. So let's say axis equals 0.01 times n hat, because n hat's the unit vector, so it's length of 1. So let's make that 100. That might be too thin. Okay, there. That looks good. Okay, and that's my x equals 1 plane. Now I can calculate the flux. So d phi is going to be equal to dot. It's going to be f. So it's going to be f of rt dot n hat times dA. And see, this was so awesome, right? Because once I start putting them, this looks just like the integral. It's f dot n hat dA. And that's the piece. And I can just add that to the total. Phi equals phi plus d phi. And that's that. Let's just run it. It's not going to give us anything. I'm not going to print it out because it's not the total flux. It doesn't matter. I don't know why it's going so slow. What did I do? N equals n plus 1. I anchored it. What did I do? Okay, let's put this at 100. Or 10 even. That one's at nf equals 100. Let's run it again. Is that what it is? I did not mean to make you angry. Okay, there. It made 1. Something happened. Dot. F dot t is not a function. Dot. F or t. That does return. Aha! No, that's fine. Let's just go up here and try this. Print f of vector 1, 1, 1. Let's just make sure that function's working. Okay, that's a problem. Let's go up here and change this to Python 3.0. There's a problem with trinket, I think. Okay, so I think that's working now. I don't need to print that. And I think down here, let's change this to, yeah, okay. So we're good. Okay, so that was the x equals 1 plane. Let's go ahead and switch to the other side and do x equals negative 1 because that's pretty easy. So I'm going to copy this. Let's put n equals 0 right here because I don't need to change any of that other stuff. So I'm going to delete that, even though I don't really need to. So let's copy all of this. Let's put a little piece of code up here. X equals 1. That's just where I know what I'm doing. I'm going to copy that. And, you know, there is nothing wrong with copy and pasting stuff multiple times. So I'm going to say x equals negative 1. If that's true, then this n hat, the only thing that's going to change is n hat is negative 1. That's it. Everything else still works. Oh, no. Down here, when I make RT, it's going to be negative 1. When I run this, I should get 2 plates like that. You can see the plates. I'm still at 100 circles per plate. See, there's my 2 sides of my cube. It looks a little weird. Looks like it's not spaced out, but let's just pretend like it's correct. Okay. Now let's do y equals 1 and then y equals negative 1. So I'm going to copy that. And then I'm going to change this to y equals 1, just as a note. And then n hat is going to be 0, 1, 0. This is going to be equal to random, 1, random. But other than that, everything is good. So let's just run it, and I should get the top part of the cube. Yeah, see, this is... that should be 0. That's what it was. This is at x equals 0, not x equals negative 1. So I'll put this over here at 0. I forgot. No, 1. I was right. I was like, that doesn't look right. And I was right. It does not look right. See? Trust your looking. Okay, so now we're getting our box, right? Okay, now I'm going to do y equals 0, not negative 1. So I'm just going to copy all this. There's nothing wrong with copying and pasting this. There's nothing wrong. Don't think I'm not a good programmer. Because you know what? I'm not a programmer. I'm a physicist. So, there. So the n hat is going to be equal to, the n hat is in the negative direction, though. And then this is going to be equal to 0 right there. And that's the only thing I have to change. I'm going to run it. Now I'll get the bottom. See, it's building up nice. And then I'm going to copy this. Let's do z equals 1. So I'm going to go up here just as a note, z equals 1. N hat is going to be equal to 0, 0, 1. The random is going to be equal to random, random, 1. And that's it. I got one more side of that box. See, it's on the back side. So let's do z equals 0. And I didn't reset phi. So once I get done, all I have to do is print out phi. and it should be the same. Let's see who does this sometimes. Okay, and I'm going to go up here and say, oh, it didn't change that. Let's just copy this. That way I only have to change it from -1 or from 1 to 0. Okay, so then up here, RT is this going to be not 1 but 0. And this unit vector is going to be -1. And then I should be done. I should have my phi. I can print that out. Print phi equals phi. Let's see if that works. Okay, we have a full cube. You see that? I didn't display the stuff on the inside. And I get things very close. Q is kind of small, but I think I'd put that back down to like 10. Ha! That's 10. Let's put this at 1,000. And let's put these other one at 1,000 too, because why the heck not? Go all out. Check that out. That's nice. Nice. And I can zoom through it. You always have to do that. It's required. Okay, just for fun. Okay, now what if I wanted to do another shape? Let's just do something like, let's see. I could do that. I think I'm not gonna do another shape right now because I don't wanna make this go on too long. But I could easily do a sphere that's gonna be one thing. Now with the sphere, each random element does have a different in-hat vector, which is just gonna be the unit vector for the piece. I think I could do it pretty quickly, but I don't think I will. I think I'm gonna leave it here. So this is part 2 of the divergence theorem, showing that the divergence, both sides of the divergence equation works even with random numbers. And that is, I think, pretty awesome. Okay. I have the code. I'm going to give you the code. You know that. Okay.